Hello and welcome. In this presentation, we're going to be talking about visual analysis of data in single case research designs. What do we need to complete this task? Well, we need visual displays. The purpose of a visual display is to organize and communicate information. Some different types of graphic displays we'll see in single case research include single line graph, which is the most common. It's how we show our replications of effect, our ongoing student data, and student performance. Complex line graphs have a number of lines on one graph, so we can display different data on the same graph to emphasize a point a lot of times of intersection. Cumulative line graph is a way to show growth over time as data are compiled at each session, including the previous session. And a bar graph is a useful tool for showing comparison of average data, perhaps before and after, or across students, generally presenting mean data. So we have a lot of different types of graphic displays you're going to see in single case research. However, the simple line graph is the primary decision maker as we observe student behavior change and make those decisions based on that. So before using visual analysis, we have to ask ourselves, are the legend axes and conditions labeled clearly? That's important information because we are able to find out what the dependent variable is by looking at the label of the y-axis, and we can determine the intervention by looking at the label of the conditions. So it's important that we have all the information on the graphs. Have we tracked the data visually to ensure that all data points are connected? Disconnected lines, data points indicate new conditions or a lapse in time. We want to know, is the scaling of the y-axis appropriate? Remember, it needs to be about a 2:3 ratio. That is, do the changes in performance appear to be commensurate with their clinical significance? Remember, minuscule changes do not appear as huge changes in behavior unless such changes would be significant. A relatively small change in the occurrence of a health or life-threatening behavior might be rather important. Conversely, a change of a few percentage points in the accuracy of solving math problems might not represent such a significant change. Do the data depict the performance of an individual or a group treated as a single student? In the latter case, is there a range of variability of the individual performance within the group also included? So here is a list of visual analysis advantages. You've seen this information before. Essentially, the advantages of visual analysis are advantages of single case research. Why? Well, because visual analysis is key to single case research. Having a graph in itself provides you with so much information. The first step in analyzing visual display of data is to determine and examine the figures for the basic variables involved in the study being presented. Dependent variable, intervention, that could lead you to the research question of the study. It tells you if there is potential evidence of experimental control. What would that entail? You got it. 3 replications of effect. Do data presented demonstrate a functional relationship between the independent variable and the dependent variable? Of course, descriptive statistics are important in the visual analysis. You still need to understand what is a mean, a median, mode, and the range. Give the definitions here, and I'm sure you're aware of these terms. The number of data points needed to provide a believable record of behavior during a given condition also depends on how many times the same condition has been repeated during the study. This says a minimum of 3 data points or until stable, but the general rule is the more the better, but as a rule, fewer data points are needed if replications of the experimental condition replicate the same level and trend in performance. Additionally, if the published literature shows that the intervention has been effective, that plays a part in determining how many data points are sufficient. The more previous studies, the less data points needed. The more data points are needed to demonstrate new findings. Now, so there are exceptions to the rule of the more data points, the better. Ethical concerns do not permit the repeated measurement of certain behaviors, such as self-injury, under an experimental condition in which there is little expectation for improvement during the baseline treatment condition. There is also little purpose in repeated measurement in situations in which the subject cannot logically perform the behavior. Asking a student to solve math problems that he or she has not been taught to solve. So we need to look at how to analyze the visual data. We have within condition analysis and between condition analysis. And really we're looking at the same features, but I'm going to go over them separately so that we can be clear. So to begin, we're going to talk about level. Level refers to the ordinate value. We want to know the level stability, and we can find that out by looking at the median level and determining what percentage of data points are within a small envelope around that median. We also want to look at level change. Absolute level change is essentially the difference between the first data point in the condition and the last. The relative level change is the median of the first half of the data and the median of the second half of the data. Level lines should be the median rather than the mean level. Because a median level line represents the most typical performance within a condition, it's not so influenced by one or two measures that fall far outside of the range of the remaining measures. So let's talk about how to calculate median level. Well, median is the middle number, right? So if we took all of these data points right here and we put them in order, the values in order, the median is the one in the middle. So in this case, 30 is your level. So we might describe that as 30, a median of 30, or we might describe it as low. So we need to get a stability envelope by determining if 80% of the points fall within 20% of the median. So if our median is 30, 20% of that would be 6. So it would be somewhere probably, well, it could be 27 to 33, but maybe 25 to 35, depending on what the possible point values could be. It looks like in this case, they're all in 10-point increments, so it makes it a little difficult, but we want to see what percentage of the data points fall within this range. And here we have about what? 1, 2, 3 out of 9. So that's 1/3. That is variable data. That is not stable. So we would need to continue this condition until we were able to find the confounding variable that is causing this instability. We want to consider trend. Trend is the overall direction taken by the data path. To look at and talk about trend direction, we want to talk about accelerating trends and decelerating trends. If there's no trend, it's zero accelerating. Sometimes if we want to be more specific, because accelerating might not really tell you if that's good or bad. It might be good for an academic behavior, but it might not be good for an aggressive behavior. So we could say it's headed in a therapeutic direction. So that wouldn't really indicate going up or down. It would indicate going in the direction you wanted it to. A contra-therapeutic direction would be going against the goal. And we want to have a trend line. Now, the least squares linear regression equation can help us find the actual trend line, but most likely we're going to be using our handy dandy software to get that trend line. If you don't have that and we're just looking at a graph in a journal article, we can do a split middle line of progress. Now this slide here shows you the directions of how to do that, but I think that I'm going to leave that up to you to decide if you want to learn how to do that, because we do have technology so easily and readily available. Now, one thing that we have to remember is that the eyeball method is a possible indicator of trend line, meaning just looking at it. For example, if we look at this data, we can see trending down, decelerating, accelerating trend. But when applying visual analysis across conditions, the overall trend may be less apparent than one might perceive at a casual glance at the data. These lines may assist the researcher in determining what trends are and whether there are changes in trend that indicate desirable or undesirable changes in the dependent variable. The steepness of the trend line may also be examined for some indicator of the strength or lack thereof of the intervention. This is another reason of the warning that graph construction on equal interval graphs can be misleading if intervals are either exceedingly large or small. So just remember that we need about a 2 to 3 ratio for our graphs. Let's look at trend direction. We eyeballed this and we could see, but if you had the trend line on the graph, you would be able to more accurately depict your trend in any given condition. Not only do we want to know about the trend direction, but we also want to be able to speak to the trend stability. So we want to know the variability around that trend line. We use the same envelope that I showed you with the median level. 20% of the median, put that number around the trend line instead of the level line though. So for example, here we have our trend lines. We would put that envelope around them to show what would be considered stable. We want 80% of the data in that envelope. So here we do not have stable decelerating data, but here this is more stable accelerating data in the intervention condition. Now, not only do we want to look at the within condition analysis, but we have between condition analysis. That's where we want to look at how many variables have changed. We only want one variable to change between conditions. We want to see the change in our trend direction, decelerating, accelerating, therapeutic, contratherapeutic. We want to see a change in our trend stability. If we have variable baseline data, it would be nice to see it during intervention go to more stable data. It would be telling if it became variable that perhaps that there are some inconsistencies with the intervention. Change in level, we can again look at absolute level change or relative level change, but in this case, looking between conditions, we would look at the last data point of the baseline condition and compare it to the first data point of the intervention condition for absolute change. For relative change, we would look at the median level of baseline compared to the median level of intervention. And then lastly, we have percentage of non-overlapping data. And that is information that can really help us determine the effectiveness of the intervention. Non-overlapping data, that's the number of data points in the second condition that do not fall within the range of the data points in the first condition. You want to divide that number by the total number of data points in the second condition and multiply by 100. So again, determine the number of data points in the intervention condition that are greater than the highest level data point in the baseline condition. 70% and greater would be reasonably effective. 90% or greater would mean that the treatment was very effective. Let's look at this example. Assume you are reviewing the results of a study you just completed. The dependent variable was the frequency of telling lies during one day. The frequency of telling lies during baseline condition was 12, 11, 10, 12, 9, 10, and 13. The frequency of telling lies following the implementation of the intervention was 10, 8, 7, 5, 4, 2, 1, and 0. Now, take a second, pause, and calculate the percentage of non-overlapping data and determine if you believe the intervention was effective based on these results. Because the study was aimed at lowering the dependent variable, you would look for the lowest level of performance during baseline, which is 9. Baseline condition, 9 is the lowest. Therefore, you would want to go on to examine the 8 data points during intervention, and you would find that only 1 data point in intervention is higher than 9. Therefore, 7 of 8 intervention data points are non-overlapping, which yields a percentage of approximately 88% of non-overlapping data. Based on the criterion that at least 70% of the intervention data should be non-overlapping, you would conclude it is an effective intervention. Because the percentage does not quite reach the 90% level, you should not conclude that it's very effective treatment. However, continued intervention data might result in achieving that 90% or better of non-overlapping data and more clearly establish performance over time. Now, let's take a second and look at this graph. What 4 things could you say about these data if you're doing a between condition analysis? Okay, well, first we could talk about level. We could talk about a change in level from about a 2 to a 9. We could say there's an immediate and abrupt change in absolute level from 1 to 9, 8-point change. We could talk about the trend, and we could say we went from a contratherapeutic direction to a therapeutic direction. We could talk about the variability of the trend. We could say it was a variable decelerating trend during baseline and a stable accelerating trend in intervention. And of course, we could talk about P&D. We would look at the highest point of data during baseline, which is 3, and we'll see how many of these intervention data points overlap. If we fall below 3, well, we see none of them fall below 3, so we could say that 1, 2, 3, 4, 5, 6, 7 are not overlapping with the baseline data. And 7 out of 7 is 100%. So this is a very effective treatment. So what are we going to use this visual analysis to do? We need some general guidelines. When are we going to change instruction or not? Well, we do want to change instruction if we get a contratherapeutic trend, if our trend is too slow, and we're not reaching our aim. Additionally, if we have variable data, we need to change something up so that we can get a cleaner look at behavior. Now, you're doing great if you have a stable therapeutic trend and you're heading toward that criterion. But you want to have at least 3 data points plotted so that you can show a trend. And variable low level early in instruction might indicate an adaptation period. So you want to give it a little more time. Now, how do we make those database decisions during instruction? Well, we want to collect data frequently, plot that performance every day, set an aim line, and monitor it as to see if it follows through. And we also want fidelity with our implementation. But once we determine that trend direction, we use, with whatever method we use, we want to determine if there's variability around our trend direction, get our level data, and compare that data to what our aim line is. So what are the pros of visual analysis? Well, it's simple. We can show robust interventions. It can include descriptive statistical analysis as well. We usually put that information on bar graphs. And we're going to look past the numerical data and look for any unusual events and outliers so that we can really tweak our interventions to be most effective for our individual students. Now, against visual analysis, some say it's not stringent enough, but we need to get more people educated and get more evidence out there with really good studies. We want to be consistent with how we are presenting our data. So that is what I have. I appreciate your attention to this presentation, and I will see you later.